Deep within a volcanic arc, superheated magmatic fluid escapes from an underlying porphyry intrusion and forces its way upward through fractures in the surrounding andesite. As this fluid ascends into the shallow crust, between 0 and 1.5 kilometers below the paleosurface, it encounters temperatures of 150 to 300 degrees Celsius. In this environment, the fluid exists as highly concentrated, intensely oxidizing sulfuric acid. This extreme acidity triggers a process called acidic leaching. The fluid reacts with the host rock, stripping away its base components. Plagioclase feldspars and mafic minerals aggressively dissolve, leaving behind nothing but a rigid, highly porous skeleton of pure silica. Geologists call this remaining skeletal rock the vuggy silica core. Because of its high porosity and extensive fracturing, this core becomes the primary physical trap where precipitating fluids will eventually deposit gold and silver. This aggressive neutralization process forms a highly predictable, concentric geometry of rock alteration. Recognizing this outward fading chemical footprint is our first macro-level vector in finding the core. The vuggy silica core and the sulfide-rich feeder structures feeding it are geographically narrow, often measuring only tens of meters across, yet they represent the absolute center of the economic target. Finding that core requires penetrating the lithocap. This is a massive, visually homogeneous umbrella of advanced argillic and argillic clay alteration that can span dozens of square kilometers outward from the center. Traditional surface mapping struggles here. When standing on the ground, the sheer scale of identical, bleached, leached clays makes isolating the narrow, central fluid conduit nearly impossible. Precision drill targeting requires cutting through this noise. We have to build a unified, three-dimensional model by intersecting surface spectral mapping, structural radar, and deep geophysics. Discovering the economic core of a high sulfidation system is a multidimensional problem. We must locate the exact point where specific physical and chemical anomalies overlap. Our first essential layer of data comes from Sentinel-2 satellite imagery. By applying principal component analysis, or PCA, we can map broad surface alteration mineralogy across the entire project area. This PC4, PC3, PC2 map translates mineral features into distinct color zones. Cyan isolates the advanced argillic zone via alunite and kalunite absorption in bands 11 and 12. Yellow and red map the iron oxide cap. White pixels identify the highly reflective vuggy silica core. Within this spectral data, alunite is highly diagnostic. Its presence is the single best spectral indicator that the extreme low pH environment required for a high sulfidation system existed here. PCA composites perfectly map the two-dimensional acidic footprint of the lithocap, but surface pixels cannot reveal the depth or exact trajectory of the vertical fluid conduits feeding it. Gold and silver mineralization relies on deep faults and breccia pipes to transport fluids upward from the intrusion. To find these vertical pathways, we layer Sentinel-1 synthetic aperture radar onto our spectral map. SAR penetrates surface vegetation to detect subtle structural lineaments hidden beneath the alteration clay. We look for a high VV-VH backscatter ratio. Radar waves bounce chaotically off the intense surface roughness of silica ledges and hydrothermal brecciation, while reflecting cleanly away from the flat, soft clay. By tracing these high-texture intersecting lineaments, we can isolate the exact structural feeder zone hiding within the broader vuggy silica anomaly.
This provides our structural framework. To confirm the system actually extends to depth, we need to measure rock density and magnetism. We now move from surface remote sensing to deep geophysical surveying. High sulfidation fluids destroy magnetism. As the acidic fluids boil upward, they convert primary magnetic minerals like magnetite into non-magnetic pyrite and clay. Because of this widespread destruction, the entire advanced argillic zone and the broader lithocap itself will register on our surveys as a massive regional magnetic low. Next, we map local gravity. The broad clay alteration zones register as a gravity low, driven by the increased porosity of the leached rock. A local gravity high, however, signals an area of dense, massive silicification. This points directly toward the hardened core. Magnetic lows outline the maximum destructive reach of the system. Local gravity highs pinpoint the dense structural center. To justify a multi-million-dollar drill campaign, we must prove two physical conditions exist simultaneously at depth: hard silica and abundant sulfides. We map this using electrical resistivity. The porous, water-saturated clays of the argillic zones are highly conductive, resulting in low resistivity readings. In this conceptual cross-section, the hard, quartz-rich vuggy silica core yields extremely high resistivity, exceeding 500 ohm meters. To find metals within that rock, we use induced polarization, or IP chargeability, calibrated to detect the presence of disseminated sulfides at depth. The host minerals for gold and silver in this system, disseminated pyrite, enargite, and covellite, hold a strong electrical charge. Their presence yields a high IP chargeability, reading greater than 40 millivolts per volt. Finding high resistivity without high IP means you have found barren silica. Drilling it is an economic failure. The definitive geophysical bullseye requires the perfect intersection: high resistivity mapping the silica trap, overlapping exactly with high IP chargeability mapping the sulfide fill. Before mobilizing a drill rig to test these physical anomalies, we must validate the target using surface geochemistry. High concentrations of highly volatile elements like mercury, antimony, and arsenic indicate you are sampling the cold, uppermost tier of the lithocap. By tracking the geochemical ratios, we can determine our position in the system. Increasing concentrations of copper, gold, silver, and tellurium indicate you are vectoring directly into the hot magmatic feeder. Finding high arsenic combined with high copper specifically points to the presence of enargite, the hallmark sulfide mineral of a high sulphidation core. Geochemical zonation proves the hydrothermal fluid was fertile. It confirms that the physical trap we mapped actually contains the metals we are trying to mine. A Priority 1 target requires the strict intersection of multiple datasets. First, surface chemistry: white and cyan pixels representing vuggy silica and advanced argillic alteration. Next, structural properties: a radar-mapped feeder lineament inside a magnetic low. Finally, the critical deep geophysics: subsurface resistivity exceeding 500 ohm meters, perfectly overlapping with IP chargeability above 40 millivolts per volt. When all these datasets align, you have a validated high-confidence location for the drill bit. High sulphidation exploration is an exercise in stripping away noise. By forcing spectral, structural, and chemical datasets to overlap, we stop guessing at surface anomalies and precisely trace the thermodynamic pathway of the gold.